We want to form a bond between carbon and bromine. We need 2 electrons for that bond. Where can we get those 2 electrons? We can get 1 electron from the carbon radical and 1 electron from the bromine-bromine bond. And we will form our product. In this video, we are going to introduce the radical halogenation reaction and talk about its mechanism. We'll start with the net reaction. The net reaction is the reaction of some kind of CH bond with an elemental halogen to produce a haloalkane and HX as a byproduct. The elemental halogen X2 can either be bromine or chlorine, and there are no other real reagents for this reaction. We just need to input a lot of energy into this reaction to get it started. We can do that in the form of light or heat. So our symbols here, H nu is the equation for the amount of energy given a specific frequency of light. And heat is thermal energy, just raising the temperature, adding thermal energy. So we can either add light or heat to this system, where we can react a CH bond with elemental halogen. A bit about my notation here for the starting material. These 3 other lines are not necessarily meant to be methyl groups. What they really represent is, okay, I understand that carbon makes 4 bonds. It doesn't really matter what's on the other side of the molecule. What we want to focus on in terms of generalizing this reaction is we're reacting some kind of CH bond. Doesn't really matter what the rest of the reagent is. We're focusing on the fact that we're reacting a CH bond with an elemental halogen to form a haloalkane and HX as a byproduct. The mechanism for this reaction is a bit unusual. I call it the IPT mechanism. There are 3 sections to this mechanism: initiation, propagation, and termination, and we'll need to include all 3 in our mechanism when we draw it. So the initiation part of the mechanism is how the mechanism gets started. Our goal of the initiation section is to form the key propagating radical. We will be forming the radical from X2. The other thing to remember is that the first initiation step always needs to have 0 radicals on the reagent side and 2 radicals on the product side. If you think about it, when we start the reaction, we don't have any radicals, so our initiation is how we're going to get the process started. It's how we're going to form our first radical. So it always goes from 0 radicals to 2 radicals in the first initiation step. The propagation step is our main product forming sequence in the reaction. Some things to remember about the propagation sequence is that every propagation step always needs to have exactly 1 radical on the reagent side and 1 radical on the product side. If you're ever doing a propagation step and you don't have 1 radical on the reagents or product side, that means you've done something wrong, and that's not the correct propagation step. The ending radical at the end of our propagation sequences can be more than 1 step, but that last radical that we form at the end of the propagation needs to be the same as the first radical that we start with in the propagation sequence. Talk about that more in a second. And finally, when we're done with the propagation, if we add up all of the propagation steps, the sum of the propagation steps needs to be the same as the net reaction. Again, we'll talk about that more when we get there. The last section of the radical mechanism is the termination. That's the cleanup phase for these reactions. That's where we take 2 radicals and we combine them to form something that has 0 radicals. One of the termination steps usually forms more of the desired product, but that's just a coincidence. When we think about these 3 sections of the radical reaction, some things to keep in mind. The initiation sequence in the radical reaction is a relatively rare event. It doesn't happen all that often. The starting materials were doing just fine being bonded together. They don't really want to form radicals. It's a high energy process. It's not very favorable. So the initiation in terms of probability doesn't happen very often. That means there's a very low concentration of radicals at any given point in the mechanism. The propagation sequence happens a lot. And the termination sequence is also a relatively rare event. So if we want to talk probabilities, I'm going to make up some numbers, but it's close enough for what we're talking about. The initiation step may happen 1% of the time. The termination step may happen 1% of the time. The propagation step happens 98% of the time when we talk about these mechanisms. The propagation is the main part of the mechanism, and it's where we want to focus. Let's actually do a radical mechanism, and we'll go through the process for the radical halogenation. We'll do a specific example where we're going to take this starting material and react it with elemental bromine with thermal energy in the form of heat. And I'm going to leave our product blank for now. We'll come back and fill those in as we go through the mechanism. So we need to include the 3 parts of the mechanism. We'll start with the initiation. The initiation is where we go from 0 radicals to 2 radicals. The initiation will target the weakest bond in all of the reagents. The weakest bond is usually a bond between 2 heteroatoms. Carbon-carbon bonds, carbon-hydrogen bonds are very strong, but bonds between 2 heteroatoms tend to be very weak, something like the bromine-bromine bond. So when we add energy, in this case in the form of heat, to this reaction, this weak bond will undergo homolytic bond cleavage. The bond will break and 1 electron will go to each of the 2 bromines and will form 2 bromine radicals. Started with 0 radicals, formed 2 radicals, formed our key X dot propagating radical. This is the initiation step for this sequence. If we go into propagation, there are going to be 2 propagation steps for this reaction. The first step, propagation step A, we're going to start with our organic starting material, and we're going to use our bromine radical to abstract a hydrogen from our starting material. One of these hydrogens is a weaker CH bond than the rest, and we will abstract that hydrogen to form the most stable carbon radical that we can. When we look at this molecule, there are lots of carbon-hydrogen bonds. We think about the resulting radical that would form when we break one of those carbon-hydrogen bonds. One of those carbon radicals will be more stable than the rest. Take a second, what do you think? Where do you think the most stable radical would be in this molecule? So if you said this position here, the position that is fully substituted, if we could get a radical there, that would be best. However, this carbon has no hydrogens attached, so we can't remove a hydrogen from this carbon because it doesn't have any hydrogens attached. The carbon here at the top of the molecule, this is going to be the place where we can get the most stable carbon radical. So we're going to abstract this hydrogen. We're going to form a bond between bromine and hydrogen. We need 2 electrons for that bond. Where can we get those 2 electrons? We can get 1 electron from the bromine radical. We can get 1 electron from the CH bond, and that will form HBr in this process. This bond has 2 electrons though, and when we do these steps, we need to account for all of these electrons. So we're going to break this bond, we're going to take that other electron and deposit locally onto that carbon. That will form a carbon-centered radical. At the tertiary position, that will be the most stable position in this molecule, and HBr will be our byproduct. This is the first propagation step. The second propagation step, we will take this carbon-centered radical and we'll react it with elemental bromine. And we're going to do another atom abstraction. We're going to use this radical to abstract bromine from Br2. We want to form a bond between carbon and bromine. We need 2 electrons for that bond. Where can we get those 2 electrons? We can get 1 electron from the carbon radical and 1 electron from the bromine-bromine bond. That will break the bromine-bromine bond. We need to account for both electrons, and so the other electron goes on to bromine. And we will form our product, and we'll form more Br dot, more bromine radical. So that tells us what the product of this reaction is going to be. The product of this reaction is going to be the alkyl halide, and our byproduct is HBr. This is the second propagation step. This completes the propagation process. So if we look over at our notes for what we need for propagation, every step of this process has 1 radical on each side of the arrow. The last radical that we form is the same as the first radical we use. And if we take the sum of these reactions and add them together, some things cancel out. So Br dot is the same on both sides, so it would cancel out. Carbon dot is the same on both sides, so it would cancel out. So the only thing left on the reagent side are the alkane and elemental bromine. The alkane and elemental bromine. The only things left on the product side are the alkyl halide and HBr. Alkyl halide and HBr. So the sum of these steps is the net reaction. It's important that the last radical is the same as the first radical because remember, the concentration of radical is very low. This initiation sequence doesn't happen that often. There's very few Br dots in solution at any given time. So for this to form the majority of our product, it needs to keep happening over and over. So any time we get 1 initiation, that Br dot can go to form the product, which forms more Br dot. This can then go back and do more propagation to form more product and another Br dot, and can go back and do another propagation and more Br dot, and this kind of keeps cycling over and over again, and this is our main product forming process in this reaction. The termination sequence, there are several possible terminations that could happen for any given radical reaction. Termination is when any 2 radicals in solution happen to find each other and combine to form a new closed shell paired electron species. The most popular one, everybody's favorite, is when 2 Br dots find each other. They form a new bond. We need 2 electrons for that bond, so we take 1 electron from each of the radicals, and we combine 2 Br dots to form Br2. It's essentially the reverse of this initiation. Remember, this process was unfavorable to begin with, and so the reverse process is favorable, as long as 2 radicals can find each other in solution. Remember, this doesn't happen very often, so the likelihood of any 2 radicals actually finding each other, actually forming a bond, is relatively rare. So Br dot is one of the radicals in solution. Carbon dot is another radical in solution, so we can take Br dot and one of the carbon radicals, and we can form a bond between bromine and carbon. We need 2 electrons for that bond, 1 from bromine, 1 from carbon, and that will form a new carbon-bromine bond. Notice that this happens to form more product, but it's just a coincidence. This is not the major product forming step in this reaction. Again, this is relatively rare. 2 radicals actually finding each other and forming a bond is relatively rare, so this process does not form the bulk of the product. The bulk of the product forms in the propagation sequence as this cycle happens over and over and over again for every 1 initiation event. Another possible termination is 2 carbon radicals finding each other. We'll form a new carbon-carbon bond. We'll take 1 electron from this carbon, 1 electron from this carbon to form a new carbon-carbon bond. and this is another possible termination product. This is the overall mechanism for this reaction. If we were asked to draw a mechanism for this reaction, we need to include all three sections, and we need to include the initiation, the propagation sequence, and the termination processes. So this is the entire mechanism. We call these types of mechanisms chain reactions, mainly because of the propagation sequence, where we start with Br dot, we form more Br dot, which can start the chain over again and form our bulk of our product. The other thing I want to point out is this propagation step B. If we're going to make a mistake in this mechanism, it's going to be here. Students will often misdraw this step. Instead of using Br2 as the intermediate, they'll use Br dot here. They'll actually do this second termination step, but they'll put it here in the propagation sequence. If we do that, if we take carbon dot and Br dot, yes, we'll form our product, but we won't form any more radical, which means it can't be a propagation step. There would be 2 radicals on the reagent side and 0 radicals on the product side. It doesn't fit the criteria of 1 radical on each side, so that can't be the correct second propagation step. So just make a note of that. Don't make the second step a termination. That's the most common error in these mechanisms, so just know about it now so you don't do it. Here is our summary card for the radical halogenation reaction. An example of the radical halogenation shown here. We have our 3-phrase sentence. 3-phrase sentences are a convenient way to organize reactions in your head. If you have to memorize something, memorize the 3-phrase sentence. The 3-phrase sentence always has the starting material, the reagent, and the product in it. So for this reaction, the 3-phrase sentence would say that an alkane plus X2 makes an alkyl halide. We need to know this 3-phrase sentence in all possible combinations. So we need to be able to say that an alkane plus X2 makes an alkyl halide, X2 turns an alkane into an alkyl halide, and an alkyl halide is made when an alkane reacts with X2. Some notes for this reaction. This really only works well for Br2, for bromine. The reaction works with Cl2, with chlorine, but the reaction is no longer selective. And the reaction fails with iodine and fluorine. In fact, if you tried to use elemental fluorine, you would probably burn down the lab. We'll talk more about that in a different video. This really only works for unsubstituted alkanes, no other functional groups. And this is actually an important point. It only works with a pure alkane, no other functional groups. No alkenes, no alkynes, no alcohols, nothing except just an alkane with carbon-hydrogen bonds. That's really the only way this reaction works well, predictably. This reaction goes through a radical intermediate. Some tags for this reaction: it is a regioselective reaction. It forms the most stable possible radical intermediate. It is not stereoselective. It's a non-stereoselective reaction. We form a mixture of enantiomers in this reaction, a mixture of stereoisomers for this reaction. And this reaction is a formal oxidation. We start at the 0 CZ bond oxidation level, and we end at the 1 CZ bond oxidation level. We move up 1 rung on the redox ladder. This is a formal oxidation.
I'm glad you're here with us for this training today. Check out these other videos in my playlists to see if there's anything else that can help you level up your ninja levels even further. As always, don't forget to like and subscribe.